Hey guys, and welcome back to another video. Today we will be performing a vacuum distillation of some store-bought 35% hydrogen peroxide to increase the concentration to approximately 95%. These concentrations of hydrogen peroxide find use as a liquid propellant in rocketry, which may be explored in a future video. Before we begin, it is important to note that hydrogen peroxide is a strong oxidizing agent that can cause severe burns or explosions in the concentrations that we will be preparing. This hydrogen peroxide is not the 3% typically found in the grocery stores and must be handled with care. Both 35% and 95% hydrogen peroxide will cause severe burns to the skin, and additionally 95% hydrogen peroxide is flammable and it can explode if heated. Furthermore, hydrogen peroxide will react with some organic solvents and form explosive peroxide, so care must be taken. Vacuum distillation can result in an implosion if damaged or incorrect glassware is used. Concentrated sulfuric acid can also cause severe burns. Gloves, a face shield, and a lab coat are mandatory, and this procedure should be performed outside in an open space in case of an explosion. Do not recreate what is seen in this video. To begin, a fractional distillation apparatus must be set up. A 500 milliliter round bottom flask with boiling chips is placed in a water bath on a hot plate, which was built in a previous video. Boiling chips are necessary to reduce the bumping and foaming during the distillation. Old pieces of broken glass were used in this case. On top of this, a 300 millimeter fractional column is clamped in place, followed by a still head with a thermocouple, condenser column, vacuum takeoff adapter, and a receiving flask. A refrigerator compressor from an old fridge is being used as the vacuum pump in this case, as it can pull a sufficiently low vacuum while being free from a junkyard. This is set up on a concrete slab in a field, away from other buildings and objects in case of an explosion. All joints are greased using 98% concentrated sulfuric acid, which was distilled in a previous video from drain cleaner. To start the purification, approximately 100 milliliters of 35% concentrated hydrogen peroxide is added to the round bottom flask. The volume should not exceed 1/4 of the flask capacity, as the mixture tends to foam quite a bit during the distillation. 1 liter of 35% hydrogen peroxide can be purchased at the health food stores for approximately $20. That's where I found mine. 3% hydrogen peroxide from a grocery store should also work. However, because its concentration is so low, very little peroxide will be obtained. The 35% concentration is much more economical. Once everything is added, the vacuum pump should be turned on, ice cold water should be flowed through the condenser, and the water bath should be slowly heated to approximately 50 or 60 degrees Celsius. Heating higher than this can increase the likelihood that the hydrogen peroxide will explosively decompose once higher concentrations are reached, so it's important to keep the temperature as low as possible. Higher temperature will also increase the decomposition of the peroxide, so lower temperatures will give a higher yield. Pure hydrogen peroxide boils at approximately 150 degrees Celsius, so water will distill over first, and the hydrogen peroxide will be concentrated in the distilling flask. Because of this, it's also important to use fresh, clean hydrogen peroxide and clean glassware to reduce the possibility of explosive organic peroxides being concentrated during the distillation. Once water begins to distill over, continue to carefully monitor the still head temperature until the temperature starts to drop. This will signify a majority of the water is distilled over and very pure hydrogen peroxide remains in the distilling flask. This purification works because hydrogen peroxide and water boil at different temperatures and do not form an azeotrope. An alternative, but very inefficient method to hydrogen peroxide purification is to fractionate the hydrogen peroxide in water by freezing. Several issues occur with this method, however. This graph exhibits both the freezing and boiling points of different concentrations of hydrogen peroxide and water. Although water freezes at 0 degrees Celsius and pure hydrogen peroxide freezes at negative 0.43 degrees Celsius, mixtures of the two freeze at much lower temperatures, down to what is called the eutectic composition, which freezes around negative 56 degrees Celsius. This eutectic point makes it challenging to separate the hydrogen peroxide and water by freezing. For example, to the left of this eutectic point, freezing a 35% hydrogen peroxide sample will cause the water to freeze out first, enriching the liquid in hydrogen peroxide until the eutectic composition is reached. Conversely, to the right of the eutectic point, freezing a 70% mixture of hydrogen peroxide will cause the hydrogen peroxide to freeze at first, reducing the concentration in the remaining liquid until once again the eutectic composition is reached in the liquid. Thus, at concentrations below the eutectic composition, hydrogen peroxide can be concentrated in a liquid, and above the eutectic composition, hydrogen peroxide can be concentrated in the frozen solid. But you cannot increase the concentration of hydrogen peroxide over the eutectic composition by freezing a sample alone. Removing water by desiccation or performing vacuum distillation would be necessary to increase the hydrogen peroxide concentration over the eutectic composition. Fractional freezing is also much slower than vacuum distillation. Alternatively, looking at the boiling point graph, The boiling point increases from pure water towards hydrogen peroxide, and no azeotrope exists between the two. An azeotrope is similar to a eutectic mixture, but refers to a constant boiling point mixture of two liquids. Because no azeotrope exists for this system, however, theoretically the hydrogen peroxide can be distilled to 100% concentration. Due to increased instability at higher concentrations, however, in practice, distilling to anhydrous hydrogen peroxide is extremely challenging. At ambient pressure, hydrogen peroxide will decompose explosively before the boiling point is reached, which is why vacuum distillation must be performed, as lower pressures reduce the temperature at which the liquid will boil at. Because the boiling point of a liquid is pressure dependent, if a stronger vacuum was generated using a better vacuum pump, the water would distill over at a lower temperature. After the first 100 milliliters had distilled over, the 500 milliliter flask was swapped out for a 500 milliliter 3-neck round bottom flask. This was to allow for easier refilling of the flask with successive additions of 35% hydrogen peroxide. 100 milliliters of 35% hydrogen peroxide was added 3 additional times for a total of 400 milliliters. Most of the water distilled over around approximately 45 degrees Celsius, and at this point the temperature started dropping, indicating the majority of the water had distilled over and very high concentration of hydrogen peroxide remained in the flask. The apparatus was cooled, the vacuum was turned off, and the concentrated hydrogen peroxide was removed. To determine the purity of this hydrogen peroxide, the density was calculated for 10 milliliters of hydrogen peroxide. 10 milliliters corresponded to a mass of 14.153 grams at 20 degrees Celsius. This correlates to approximately 95% purity, which is quite high purity hydrogen peroxide. To do a crude test of the oxidizing capability of this hydrogen peroxide, a few milliliters can be added to a piece of cotton. Lighting the cotton on fire exhibits the oxidizing capability of the hydrogen peroxide as the cotton pad rapidly burns, leaving very little residue. If you were to use a normal cotton pad not soaked in hydrogen peroxide, it would burn a bit and leave lots of ash. You can clearly see how much this speeds up the burning of this cotton. In total, approximately 50 milliliters of 95% hydrogen peroxide was obtained. Based on the starting 400 milliliters of 35% peroxide, approximately 145 milliliters of concentrated hydrogen peroxide should have been obtained. This means that around a third of it decomposed during the distillation. Performing the distillation under a stronger vacuum at lower temperatures would likely decrease the amount of decomposition that occurs. As mentioned at the start of this video, this peroxide is extremely dangerous and should be handled carefully and stored at low temperatures away from other organic solvents. Anyhow, I hope you guys enjoyed this project, and I'll see you in a future video.